Well, thank you. First of all, thanks very much to Michael and Simon for the chance to come here and hang out with the superstars of Ultracold Molecules. This is very exciting. It's great to see, excuse me, it's wonderful to see the collection of old friends here, many of whom I've been talking with about molecules for many, many years. And, and looking out, I feel like you guys will indulge me if I say something a little offbeat. And so let's go. First, I want to acknowledge that what I'm talking about today is the work of, not that, but the work of Kevin Xu, a current graduate student in my group, and of Ruben Wong, many of whom you know, who is now a postdoc at what remains of the ITAMP. And so the title of the talk is The Limits of Long-Range Thinking, which I'm sorry, Google wants to help me with my talk now. The title of the talk is The Limits of Long-Range Thinking, which sounds like an investment seminar. And in a sense, maybe it is. But what it's really about, as you can guess, is the idea of long-range forces versus short-range forces in thinking about molecular collisions. Here's a very much over-schematic picture of the interaction potential between two molecules or whatever as a function of distance. Of course, the real thing is much more complicated, but what one does, the way one thinks about these problems is to draw a line somewhere, there's a line, and to say, well, if the molecules are closer together than that distance, then you're in the short range limit. Potentials are deep, kinetic energies are high, things are violent. If there were two molecules that started before the collision, by the time they get together, that's a legitimate four-body problem with lots of energy being exchanged, angular momentum. It's complicated. It's where chemical reactions happen. And this is the kind of thing you would think about if you want to do ultra-cold chemistry, which many people do. On the other side of the line, we have the long-range physics. The forces are relatively gentle. The potentials are not as deep. I think of this more as a two-body system, one molecule here and one molecule here. They might have additional quantum numbers beyond atoms. That's okay, but it's two-body scattering. The forces are well known, easy to characterize. And this is the kind of interaction, the place you would live if you're doing condensed matter physics. You love the dipole interaction because altogether it's long range and anisotropic, right? We all say that. And in a scattering problem, of course, you tend to see both of them. The idea, the original idea for a talk like this was I was going to come in and say, well, there are some examples, drawn from recent experience where sometimes you get the physics right by thinking only in terms of the long-range physics, and it works out just fine. Shielding is a great example, by the way. We've heard about that earlier today. And sometimes you just got to deal with the short-range physics. And let's look at some examples of both those types there. I had a long list of examples, but you know what? That would take until dinner time. And so I've limited it now to just two examples. One where long-range physics works, and one where you need to think more about short-range physics. The first one is about entanglement and decoherence in collision processes of carefully prepared molecules. And the second one is sticky collisions, which you've heard a little bit about earlier today. So the first one is based on recent experimental work on KRB in June's lab. Tim talked about that earlier today. If there are any difficult questions, please address them to him. And so in these molecules, which are fermions, they prepare, this is such a wild experiment, there's so much going on. What they do is they have molecules, they put them in an electric field, so there's some dipoles induced in the molecules. They take two states of the molecules, the rotational ground state, n equals 0, and the rotational one-th excited state, n equals 1. And the little tilde over them reminds you that they are actually dressed by this DC electric field. And of course, in the world of condensed matter physics, the only kind of two-level system that there is a spin system. And so it doesn't matter that these were rotational states of the molecule. Now they are spin down and spin up. And this is how you talk about them, especially in a many-body context. And of course, we've seen that earlier today. The dipole moments of these things, and significantly the matrix elements of interaction of the dipole interaction are tunable by electric fields. So I have variable two-body long-range Hamiltonian between these molecules should they interact. The dipole interactions, let's think about this. I have a spin 1/2 system and I have dipole interactions. That's a magnet. And so you can study, you can model, you can quantum simulate all kinds of magnetic phenomena in this. For example, if the molecules are bouncing around on a lattice, you have something called the XXY model. I have no idea what that is, but Lawrence just described it. Thank you, Lawrence. If there are any difficult questions about the XXY model, I guess it is. Should that be XXZ? Probably that should be, I don't know. Anyway, it doesn't matter. I don't understand any of that. But there's another version of this where there's no lattice present, where the molecules are just free to roam around. They're still magnetic. They're still interacting. And in condensed matter physics, this is something you would call itinerant magnetism. The magnetic objects are just free to move around. They're not locked to lattice sites or hopping from one lattice site to another. That's a legitimate thing. And again, I'm not going to really look at the magnetic properties of this. I'm a collisions guy. And so to me, the question is what happens when these guys collide. So I should say, in the experiment, what they're interested in are superpositions. They're interested in constructing this crazy many-body Hamiltonian by means of the electric field, but then you want to see its dynamics. And to create dynamics, they superpose the molecule into an equal superposition of the two internal spin states. They let it go, and many-body physics causes that originally coherent state to decohere. And in my context today, I'll do it in the itinerant case, just molecules colliding, decohering with one another. So here's the process. Here are two molecules, and they're prepared in this superposition state of n equals 0 and n equals 1. And I've tried to suggest that by putting this yellow halo around it to make them look interesting. There they are in the superposition state. They collide, and the collision is pow. It's a little pow. Why? Because they collide at long range by weak forces. Little pow, keep that in mind. And afterwards, they come out, they're entangled. And the red things here are meant to indicate that these molecules know about each other in an entanglement sense. They drift further apart, and they're still entangled. My goodness, I guess that's how entanglement works. And then later on, you make another measurement of the molecule to see how coherent it is later. It was prepared in a coherent state. Is it still coherent later? No. You make a one-body measurement of the state of the molecule here, and you get a result. In math, it looks like this. When I started out here, each of these molecules is in a pure state density matrix corresponding to this yellow state. So they're the same for both molecules, 1 and 2. After the collision, the two-body density matrix is influenced by the scattering matrix of the process. And then I only measure one at the end, and so what I see is a reduced density matrix of one of the molecules having traced out the degrees of freedom of the one that I don't see. This is the math. And so here's how it works under the hood. I have, again, here's a schematic pair of potentials between molecules as a function of the distance. These are long-range potentials, and they're long-range for the following reason. If I have the molecules in some superposition, and they encounter one another, they are both in the same superposition state, which means if I try to project into the individual particle quantum numbers like this, I get either, in this language, I get, hold on there, fella, I get up, up, I get down, down, or I get the symmetric linear combination of these things. I'm entitled only to the triplet combinations of the two spins. And so I take this initial superposition, they're about to collide, I translate into this basis where the scattering makes perfect sense. I can work out the interaction potentials between molecules in these two states. They're a little different for the up, up, down, down than they are for the m equals 0 part of the triplet there. And that's indicated here. They have slightly different potentials. These potentials, their heights and their strengths are tunable by the electric field interaction. But they will have different scattering phase shifts. And you can work these out. Because we're at long-range physics, oh, I'm sorry, there's one other thing. These are in symmetric combinations of the internal state. The molecules are fermions, and therefore they must have a centrifugal repulsion. So these curves are repulsive at the longest range, then dipolar and whatever. And so this is strictly a long-range interaction. I can evaluate the matrix elements of the dipole-dipole interaction in this basis. That's the Bourne approximation for scattering. I can work out the phase shifts for this in the Bourne approximation. I get formulas for it. And that's nice. It comes out very, very simple. These guys collide at triplets. And so after the collision, the reduced density matrix has this form in terms of the difference between the two phase shifts in the two different kinds of channels here. All this you can just work out. You write down formulas all day long and find the electric field dependence. They're complicated, ugly formulas, and I don't put them down the screen, but they're formulas nonetheless. And so using this, you could track the decoherence of the molecules as time goes by, as collisions go by. Well, but there's one other trick here. And the other trick is there's also a singlet channel possible where the molecules are in the antisymmetric state of the spin singlet. And in that case, because they're antisymmetric, they can collide with no angular momentum, and the long-range potential looks like this and comes down, 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 and oh no repulsion there. It takes you down to where chemical reactions or sticking or whatever it is happens to these molecules. These particular molecules are reactive, in which case, pow, big pow, because this is the energetic chemical reaction down here. And in that case, the reaction, or whatever it is, removes the molecules altogether from the system. This is your one concession to short-range physics, is that something happens down there, but I'm not modeling it in any kind of detail at all. There is a collision rate for reactions, which you can get from wherever. And so the process actually looks like this. You start with a gas where all the molecules are put in this superposition state given by the yellow halo. They're in identical states. They collide, pow, by some kind of long-range elastic scattering. They're entangled, according to the reduced density matrix we had before. They drift apart like this. And then, you know what? There's another molecule out there. There it is. That's one of the original molecules in the original superposition state. Hasn't collided with anything yet. And one thing you can be sure of is that this molecule is in a different state from this one, and therefore projects onto the singlet part of the scattering, and therefore, pow, as a chemical reaction, right? So there are two different kinds of scattering going on here. One that simply decoheres, and one that removes the molecules altogether from the experiment. Now, taking those two things into account, Rubin ran a Monte Carlo simulation for this, and it comes out a little bit like this. Here's the measure of coherence on this axis over here, and here's time going by over here. Jeez, here's time going by over here. My goodness. And there are two curves shown here. This is just to illustrate the significance of the collisions. So this red curve is just plain decoherence. That's saying molecules in the original superposition state just collide with each other, and I kind of never think of them again. I never think of them, I never let them have a second collision, because this is over some small number of collision times. So there's a decoherence per first collision, per pow, the little collision, and that's it. I'm seeing only the loss of coherence. There it goes. It drops exponentially as a function of time. In the other case, the black curve, which is more realistic, the two molecules in their original superpositions collide with each other, pow. They're produced in an entangled state. They hit another molecule, one of the original molecules, pow, chemistry happens, and they're removed. And that means once the chemistry happens and that molecule is removed, you don't see it anymore. Even though it had decohered, you don't measure it as decohering. So the molecules you measure are the ones that remain and survive the second collision. And the result is you see more coherence for a longer time, the black curve, based on the fact that some of the decohered molecules that you would have seen are now being removed from the trap by the other collisions. And Rubin calls this auto-selection, that the molecules are deciding for themselves to select the ones that remain coherent, even though the total molecule number is going away because of the chemical reactions. The ones that remain more coherent. So that's a not insignificant effect. You've got to put that into account to try to model things. And there's triplet. There's the singlet, in case you didn't catch that. And so you look at this black curve, which is the one that should correspond to the experiment. It's a decay of some sort. It's almost exponential, but it turns out it's actually a stretched exponential. But that's okay. You can fit to this curve. You can extract the collision rate there. You normalize the collision rate because it goes faster at higher density. So you normalize the collision rate and you extract a constant kappa, which is the density normalized rate, and then maybe there's an offset for fitting. So this is the quantity of interest. We'll take this kappa. This is what the experiment reported, and here it is. So this is the value of kappa that talks about the decoherence rate. Here's the electric field on this axis, and here's the curve that Rubin created from the Monte Carlo, this black curve, and here's the data sitting on top of it. So I don't want to make a huge big deal out of this, except to say, well, what does it mean? Over here at small electric fields, decoherence happens rapidly because there's a big mismatch between the two components of singlet-triplet scattering. Over here, there's a lot of decoherence. There's a magic spot in the middle where the two different phase shifts for the two different components of the triplet scattering are equal, and the decoherence is sent to zero there. That's the same as the Heisenberg point that Tim alluded to earlier. But the only point here is that simply this is done entirely thinking in long-range physics. This is an experiment. It's not just collision cross-sections and rethermalization things, which we've done a lot of. This is something a little finer, a little bit more like entanglement and cool quantum stuff, described adequately by long-range physics alone. That was the first part. Here comes the intermission. And then the second part begins. We'll talk a little bit about sticky collisions. This has been alluded to earlier today. They are two-body collisions that produce loss in molecules, even in species that are not chemically reactive. We know that, thanks to the work of Arthur and Tice, we know that light from the optical trap contributes a lot to this loss from these complexes. But here's the catch. Even if you turn the light off, there's been experiments, I think Simons remains kind of the gold standard here. You turn the light off and ask how fast are the collision complexes decaying by themselves without being destroyed by the light. You still get lifetimes on the order of milliseconds, which is quite long. And it's still an open question how to account for these lifetimes. Well, here's attempt number 3. Oh, let's see. Did I have? Well, okay, here's the picture of it, the schematic picture. And this picture's been up here earlier today, too. Here's the interaction potential between, in this case, an atom and a molecule. They meet in the ground state because that's kind of an ultra-cold collision thing. And they come in here. There are lots of other channels they could go into. Some represent rotational excitation of the molecule, some vibrational excitation of the molecule. And the idea, the story we tell ourselves, is that molecules come in on the initial channel, they boink, they jump up into one of these states and bounce around for a while, and then they try to get back out. No, boink, they jump into another one. And then boink, 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 they keep jumping around in all these states here. There's only one state they can get into that gets them out again. And so the lifetime, the amount of time they spend boinking back and forth in this complex is proportional to the density of states. The more states there are to go boink, boink, boink in, the longer they spend back there. And it leads to a quantitative estimate, a number, the RRKM lifetime. That's based on simple statistical ideas, and it's not great. We've done some work on this, along with Goulvan here and with James Croft. We've written a trilogy of papers here on sticking, looking at various aspects of it without really getting anywhere. I feel like these papers would have been much more popular if we had included more vampires, frankly, but there it is. One of the things that you learn about the RRKM theory of lifetime is that it is inadequate, among other things. One thing is, it's a statistical theory. In order for this to make sense, you're averaging over many, many resonances. That means the energy range that you're exploring has to include lots and lots of resonance states. But you know what? The energy range you're over is, let's face it, 100 nanokelvin or whatever it is. Not many resonances fit into 100 nanokelvin in most molecules. So there's no averaging to be done. The theory doesn't make sense from the beginning. And yet we wrote 3 papers about it. Yeah, good for us. All right. Good for us. The other thing is the RRKM lifetime is a number. If you know the density of states, and a lot of these molecules, you do know the density of states, you calculate a lifetime, you don't know what to expect of that lifetime. How close would the experiment have to come to that number for you to say that the theory is a success? What you want is the distribution of lifetimes, if you could get it, and understand, give an uncertainty estimate to it. And it ignores the physics of the complex itself. It's the limit of long-range thinking, and this is one of the main points here. follow me now, if you will. Here's the schematic picture of potentials and whatever, and I'm going to say the following. So we just goof around when we do these calculations. But suppose you were the world's best chemist, and many of you are, in fact, the world's best chemists here. You create a super accurate potential energy surface. You do super detailed close coupling calculations, which I represent by this because I have no idea how they work, but I know they exist. You can do real solid calculations that include all the physics you can possibly think of that lives here in the short range. And the result of that is an S matrix at the end, a scattering matrix that's full of resonances. How many resonances? Well, probably corresponds to the density of states. And so the thing I want to emphasize is, even though you've put all your effort into all this short-range physics, the viewpoint you have at the end is kind of a long-range thing. You're seeing asymptotically the effect of this scattering in the S matrix. What you can do with that is calculate the Wigner-Smith time delay. This is an old and beloved trick in quantum physics. You have a resonant spectrum. You take this combination of the S matrix, and you get lifetimes out of that. And you can go in and try to calculate for real the lifetime of these complexes. Well, this was done actually. Here's one example. James Croft and collaborators did this in rubidium plus K2. This is not ultra cold. Their energy range is now here over Kelvin, not nanokelvin or microkelvin. Here's the lifetime. This is exactly the time delay I was talking about there. You see the resonances there. You see that the typical time scale for this calculation is on the order of nanoseconds, although some of the resonant peaks go off scale. They're quite a bit higher. But the average, the thermal average of this, turns out to be a nanosecond. This is a case where, seeing all the resonances, you get the RRKM estimate is actually quite good compared to the time delay you get by detailed scattering calculations. That's promising, but that's one calculation in one molecule. So here's what we propose. We have the schematic picture of some potential energy surface that I don't know how to calculate, and I mean, you can do it. You do a calculation for a year, get an answer, go back to another calculation for a year, get another answer. That's the kind of calculation this is. If it's me, I say, well, look, I'll fill space back here with resonances. I know the density of states of the resonances. I can postulate coupling strength from the bound states to the continuum. I can just write down a short range K matrix. If you don't do scattering theory for a living, it's related to the S matrix. It's full of resonances. You can see the poles there. You can propagate those trivially to long range. And the result is you get an S matrix full of resonances. You get the same kind of answer that you would get doing the full calculation over and over again. Instead of doing 1 year per calculation, you can do 100 of these in a second and start to collect statistics. So we are making a model. We are modeling quantum chemists, is basically what we're doing. We're replacing the work of the quantum chemist by some schematic thing here that qualitatively is about right. It's got the density of states in it, for sure. And you can calculate the time delay from that. And so you're taking statistics over, if you like, ensembles of hypothetical molecules. Each calculation on each different molecule would be the same. You reduce them to a common denominator by putting them in some reduced units, which are, in our case, the van der Waals units. Here's what you get. So here's a case where we call dense resonances, where actually KT, the temperature range, does contain several resonances, like rubidium cesium is in this limit. And here's just one of the sample spectra. Here's energy, whoops, that's not right. Here's energy on this axis in units of the van der Waals energy. And in this experiment, the temperature is not too far off from that, so this is realistic. The red curve is the Maxwell-Boltzmann distribution at that temperature, and you see the resonance spectrum in terms of time delays here, also in reduced units. And you calculate the time delay from this, you thermal average it, you do it a bunch of times, and you get statistics. There it is. Here's a histogram of the possible time delays in these reduced units. Helpfully, the red line here shows the RRKM value. The mean of this distribution is close to the RRKM. It actually works if you can average over things. There's a width to this distribution, which scales roughly as the square root of d over kt. And one point to take away from this is, well, in this case, which is geared to look like rubidium, even though it's in reduced units, it's meant to look like rubidium cesium. You get the RKM lifetime plus or minus, let's say 20%. Now you've got something meaningful to compare to the experiment, which, I remind you, was not within 20%. It's more like a factor of 2, right? So that's a failing of this model. And then you go back and try to fix that model. The other case that's kind of interesting is the sparse case, like an atom-molecule situation. Same thing, we're showing the energy here on this axis, thermal Maxwell-Boltzmann distribution there, and a time delay. And if you go through it, the time delay has a threshold behavior that's kind of 1 over the square root of energy. Depends on the coupling, depends on whatever. But the point is, here's a case where within the range KT, there's almost never a resonance. The nearest resonance is far away. And you start going through statistics of this, you get plots like this. I regret we don't understand these distributions more than we do, but the fact is the resonance could be on this side of 0 of energy, could be on this side of 0 of energy. The time delay could be either positive or negative. The mean value is 0 for this. We see this pretty consistently in the distributions. If you change the energy range or the temperature range, you get weird asymmetric things. So I'm not ready to draw conclusions from this yet, except that, again, if you convert this into real units, it falls far short of the measured lifetime of the rubidium KRB molecules. But with these distributions, we can start to look closer into why. All right, so that's the end. My red light is flashing. So I'll just take to summarize. Sometimes you feel like a nut, and sometimes you don't. When do you not feel like a nut? Well, the entanglement stuff with KRB actually works really well. You can think purely in terms of long-range physics. The decoherence is working just fine. That was a case where chemistry was taking molecules out. We're not shielding in that case, but you could. You could imagine going to a situation where you shield against chemical collisions. You have only the decohering collisions, and you're making a model for the growth of entanglement of a gas of molecules. That's the next step Ruben is looking at. When do you feel like a nut? Well, come on. If I think in this long-range sense, if I look only at the S matrix, no matter where it came from, no matter how good it is, it may not still help me understand. I have to look even harder at what exactly is going on in the complex to understand sticking. And I'll stop there. Thank you.
John, thanks a lot for this nice talk. I'm sure there are questions. We start up front here with Jeremy.
Go for it. Oh, I'm sorry.
Oh, sorry.
Oh, okay. Then
I'm sorry, I saw Timur.
no problem.
I'll be brief to let.
Timur has the cube.
Can you hear me?
Yes.
All right. So one of the things that could be missing in the, if you go back to the K matrix formula, is that the fact that the poles in the S matrix do not necessarily have to be isolated, and the poles can merge. And then the formula that you have for the K matrix with this, numerator W squared over E minus ER would have to be replaced by something which has like the physics of the merging poles. That would be there in a couple channel calculation, but it seems to be, I don't know how it might help, but it could lead to things like BICs, bound states in the continuum, and other interesting things that seem to be not present in, or maybe, I don't know, it might be helpful to include.
So that's interesting. So yeah, so by merge, you mean more or less accidental degeneracy?
If the two poles coincide, you do not get the physics of an isolated narrow resonance, right? And then you get bound state in the continuum because they can merge and borrow intensity
you'll get
from one another, and they get super narrow states.
It's like a dark state.
Like Friedrich Windgen kind of states.
Yeah.
And so that could be an interesting thing to maybe try and include them in your model.
Sure. So tell me, how likely is that to occur?
Only a couple channel calculations can tell you.
Is it 1% of them? Is it 90%?
The thing is that these states have not been observed, as far as I know, in ultracold atoms. Some people, like James Croft, has a recent paper on the possibility of observing them in their colliders, but it turns to be not so easy.
Yeah.
But because of the huge density of states, they can just accidentally get on top of each other, and they can interfere.
Sure. So, okay, all right. I have another point, but we can talk at the coffee break.
So two things, I think. The first is when you model the short-range K-matrix in that way, you're modeling it as a sum, and do you have to assume a distribution of, widths of the states at short range before you get anything out for the states at long range?
Yes. So this is
Okay.
the additional point. Yeah.
Yeah,
So
okay.
one thing. So what do we do? We're basing everything on random matrix theory.
Yeah.
Because it's a very fine place to start. So the energies are chosen so that they satisfy the Gaussian orthogonal ensemble. So no two resonances accidentally close together, right? And the widths are normal distributed,
Okay.
not the logarithms of the width, as
Yeah.
you were pointing out earlier. Yeah.
So the other thing is, I mean, we looked at Wigner time delays as a function of energy on the scale of the van der Waals energy. When you're at energies well above the van der Waals energy, so your C functions of 1, then you get these nice Gaussian peaks. But when you're at energies, collision energies lower than that, then it transitions through something asymmetric to something that's just proportional to the scattering length, so that in the low energy regime, you simply have equal amounts of positive and negative, and the average over resonance is 0.
Exactly. Yeah. Yeah. So that's what we have here. So
But that's an energy, that's a difference in collision energy, not a difference in number of resonances within your collision energy.
but maybe I don't understand what you're saying, but here we get this distribution. The mean of this distribution is 0. And I think it's for that reason.
Okay, but that happens for any single resonance when your collision energy is much less than the van der Waals energy. It also happens for any group of resonances. Whereas if your collision energy is above the van der Waals energy, the transition between the two, but you get to a set of Gaussian peaks.
Okay.
We need to talk about this.
I'm not quite sure I'm following. Yeah.
Okay, thank you. There's another question. I think we can take one more. We're a bit behind, but I think.
Thank you very much for the interesting presentation. I have a question on the first part, actually, of the talk, where you discuss coherence, because the way I see it is that you will lose the entanglement of the particle when you actually do like reactive collision, because I think that you will project to one of the states of the you have, right? So I want exactly to understand what exactly you mean with coherence in this case.
So I don't know if this answers it, but you think of this as a spin 1/2 system, and you measure the length of the block vector, and it gets smaller and smaller, and that's decohering.
Yes. So this is what the one body observable essentially, right?
Yes.
Okay. So somehow like the idea. So in for instance, like cold atoms, when I started. Actually, this was back on when I started my PhD. We have this kind of like very difficult thing that we have like very heavy calculations for solitons, and what we are seeing there is actually that you should never see solitons because they actually decay so fast, and then they become very, very wide. And but of course, we all know that people see solitons in experiments. And the idea is if somehow the system by three-body collisions was always being projected to the Gross-Pitaevsky state, and then for this reason you were actually like seeing something like this. Do you think that you can more or less try to access this question maybe with more controllable systems?
I don't know. These are not solitons. I think I'm not quite sure I understand what you're driving at. Maybe we can talk
Yes.
afterwards. Yeah.
Thank you very much.
Okay, there's no really urgent question. Let's thank John again. Thank you very much.